is electrostatics. So we'll go into the foundations and start with Maxwell's equations, which are the general equations for electromagnetic phenomena, and we will simplify them for the electrostatic case, which is electric flow and electrostatics. And finally, we will derive the finite element formulation to obtain the weak form, and I'll give a few hints on modeling electrostatics. So Maxwell's equations describe electromagnetic wave propagation. We have the four equations containing our relevant quantities. So when we go into electromagnetics, we have to deal with the magnetic flux density B, the magnetic field intensity H, and the electric flux density and D, and similarly the electric field intensity E. And finally, we have the electric current density denoted by J, and the electric charge density denoted by QE. The units here are given in SI units, and in fact, Maxwell's equations were based on empirical laws by Ampere, Faraday, and Gauss. So the first equation here, the curl of H equals J, is Ampere's law. Faraday's law of induction relates the curl of the electric field to the time derivative of the magnetic field, magnetic flux density, and Gauss' law describes the divergence of the dielectric field intensity, so the electric flux density equal to the charge density. And finally, Maxwell's contribution to these equations was the last equation, saying that the magnetic field is a pure solenoidal field, so its divergence is zero. And also Maxwell added the displacement current density, so the time derivative of the electric flux density, to Ampere's law to describe the final electromagnetic wave formulation, that also this term allows us to model capacitors. Okay, so the Maxwell's equations are the basis for our electrostatic formulation. However, they are not closed like this. They also, in the usual case, we need constitutive relations relating the quantities in these equations. So what constitutive relations do we have relevant for Maxwell's equations? We have first Ohm's law in the general form, relating the current density to the electric field with the electric conductivity. We have a relation between the electric flux density and the electric field intensity, which is given by the electric permittivity. And similarly, we have a relation between magnetic flux density and magnetic field intensity given by the magnetic permeability. In general, these equations are highly nonlinear. So the electric polarization and the magnetic polarization are usually field dependent. So it's also often the case for magnetic materials that we have hysteretic behavior. Also, the constitutive relations may be temperature dependent, so this will lead to a coupling to the thermal field, which we will not consider in this course, however. And in general, these relations are anisotropic. For example, for piezoelectric materials or grain-oriented electrical steel sheets used in transformers, we actually have to relate the two vectorial quantities of field density and intensity by a tensor of rank 2. So let's simplify our Maxwell's equations for the steady state or stationary case. So if we consider time-independent problems, we simply set our time derivatives to 0. And thereby, we first neglect the influence of eddy currents. And of course, we can't consider electromagnetic waves. And what also happens by this simplification is that we can actually decouple the electric and magnetic fields. And we can then differentiate the following sub-problems. First is the electrostatic field in isolators without free charges. And the second sub-problem is electric flow, so current conduction by stationary charge transport through electric conductors. And both problems we'll now look at a bit more in detail. What we need in this case is the electric potential. So if we take Faraday's law, one part of the Maxwell's equations, curl of E equals the time derivative of B, and we only consider the stationary case, so we set the time derivative to 0, we have the curl of E equals 0. And this, we can see, is identically fulfilled if we introduce the so-called electric scalar potential phi, and if we simply define the electric field by the gradient of this potential. And due to convention, we use the minus sign. So E is minus gradient of phi. And why is the equation identically fulfilled? Simply by the calculus relation that the curl of a gradient is 0 all the time. So with this, we have satisfied the stationary version of Faraday's law. So what equations remain to satisfy? Let's look into the electric flow equation first. So when we take the divergence of Ampere's law, given here in the equation, we just put the divergence in front of everything. And then we use Gauss' law and the general Ohm's law. We simply insert here, and also we neglect. And then we can obtain a conservation equation for the electric charges. So this is how the equation simplifies if we also introduce the electric potential in order to satisfy Faraday's law. The term with H, so divergence of curl of H, vanished since another calculus relation, the divergence of eddy curl is 0. And we can see that Faraday's law in its stationary form is enforced by using the electropotential. So we have enforced two equations at the same time by introducing the electric potential. We can also see that this actually, again, has the characteristic form of a conservation equation. We have the time derivative of the conserved quantity and the divergence of the flux of the divergence of the conserved quantity. Okay, so how does the partial differential equation now look like, the strong form that we want to solve? We restrict ourselves to stationary current transport, so the time derivative drops. So we have the divergence of gamma times gradient of phi equals 0. And then we can define, as usual, boundary conditions of Dirichlet type and of Neumann type. What do they physically mean? Physically we can set known electric potentials at boundaries, or we can describe the normal component of the current density entering or leaving via the boundary is Jn. And what we can also see here, that this partial differential equation for electric flow is mathematically equivalent to stationary heat conduction. So in fact, we don't have to derive the finite element formulation. Once again, we have already done it for heat conduction, so the procedure is exactly equivalent. So what do we need as a material parameter for electric flow? We need the electric conductivity, which by Ohm's law relates the current density to the electric field. We can see that since it relates to vector valued quantities, it has to be in general a tensor of rank 2, because our medium might be anisotropic. For most metals, however, we can consider them as isotropic, and then the electric current density can be considered as a scalar quantity or a tensor with equal diagonal entries only. The main dependence of the electric conductivity is on temperature. So if we want to consider temperature, we can introduce a coupling to the thermal field by the material parameter of the electric conductivity. Okay, so let's go into the electrostatic field next. To derive the governing equations, we have again to pose some assumptions. Since it's called electrostatics, we consider stationary field only, so all time derivatives are 0. And the next assumption is we only consider non-conductive materials, so electric isolators. That means we have 0 free charge QE. And we also restrict ourselves now to a linear constitutive relation. So we assume the constitutive relation D equals epsilon times E. Again, our epsilon is a rank 2 tensor in general. And if we use these assumptions and plug them into Maxwell's equations, we obtain the following. We obtain the curl of E is equal 0 and divergence of D is equal 0. So how does this give us a single equation? As usual, we introduce the electric potential to solve equation 35, so the curl of E, and then we plug this assumption together with our material model into Gauss' law, so the divergence of D. So this is what we've done here: introduce the electric potential to satisfy Faraday's law, insert the material law, and we obtain our partial differential equation. Again, very similar to the electric flow case. We have the divergence of epsilon times the gradient of phi equals 0. Again, we have our Dirichlet boundary conditions directly specifying the potential on the boundary, or we have Neumann type boundary conditions defining the flux over the boundary, and this has to equal the so-called surface charge density on the boundary. So physically, these Dirichlet and Neumann conditions means prescribed electric charges or known surface charge densities on the boundaries. And again, we see that the electrostatic PDE is mathematically equivalent to stationary heat conduction, and thereby also to the electric flow problem, of course. So let's see how we can derive. First, we have to consider the electric permittivity, which is now the only difference to the other two equations, heat equation and electric flow PDE. this is simply the different material parameter. So the electrostatic PDE needs the electric permittivity as a material parameter, which relates electric flux density and electric field intensity. And typically in vacuum, we have a scalar quantity. We have the vacuum permittivity, is usually denoted with epsilon 0. The value is 8.854 picofarad per meter. And it is related to the magnetic permeability and the speed of light in vacuum by the given relation here. And often the permittivity of materials is defined as a relative permittivity with respect to this vacuum permittivity epsilon 0. So usually we have epsilon as our material parameter equals epsilon 0 times the relative permittivity. Again, the electric permittivity is in general a rank 2 tensor because it's relating to vector valued quantities. Okay, so now we're ready to derive the finite element formulation for electric flow. First, the procedure is as usual. We introduce a test function, multiply and integrate over the domain. We apply the divergence theorem and incorporate Neumann boundary conditions. So if we do this, is equivalent to the heat equation. Our weak form reads, find the electric potential phi such that we have satisfied our equation 38 for all test functions phi prime of x. And in addition, of course, we have to fulfill the essential Dirichlet boundary conditions too. This is equivalent for electrostatics. You see not so much changed except the name of the material parameter and the name of the right-hand side term, which are now electric permittivity and surface charge density. So the procedure is exactly equivalent for electrostatics. Okay, so how do we model electrostatics? First, we have to remember that we model electric isolators only. The electric potential of usually is defined on the boundary with the conductor. So if we prescribe on the boundary a constant electric potential, that means that we have assumed this conductor is ideal. That means with infinite conductivity. This is usually very good assumption, since when we consider isolators, any conductor has in relation a very high, so almost infinite conductivity. What we also have to remember is our primary variable is the electric potential, and we can use standard nodal finite elements as we could use for heat conduction. So what boundary conditions do we usually set? We have the prescribed potential either in the homogeneous Dirichlet or inhomogeneous Dirichlet form. We have the surface charge density. This is the inhomogeneous boundary condition. There often one needs to define the total charge over the electrode. Will simply simply divide the charge density by the area, or the total charge by the area. You get the charge density, and also the natural boundary condition is the homogeneous Neumann boundary condition as usual. This is enforced naturally and means zero surface charge density, or the electric flux is parallel to the boundary. And finally, we have a constant potential boundary condition if we have, for example, boundaries with conductors, but we don't know the unknown, the electric potential there, we can incorporate such a boundary conditions by introducing constraint equations, constraining all the unknowns to a single but unknown value. What output quantities do we have in electrostatics? Of course, we have the electric potential as the primary nodal solution variable. We have the electric field intensity as a derived result as the gradient of phi, negative because of convention. We have the electric flux density, which is field intensity times epsilon. And we have, for example, the electric energy density as a post-processing quantities of derived results. We can also take the electric energy density and integrate it over a region to obtain integrated region results, the total electric energy in the domain, for example, or in a part of the domain. We have the charge density, which we can get on the surface as a surface result. And we have, for example, the charge as an integrated surface area result.